partition on the sample space. Okay, and conversely, if I have a partition, then I can define a statistic for which this will be the partition. So there is a correspondence between them. Of course, those sufficient statistics can be many, but they will be functions, one-to-one functions of each other. Based on this, we have seen the concept of reduction of a partition. So a partition P2 is a reduction of partition P1 if the function which is inducing partition P1 is a function of partition function of statistics which induces partition P2. Okay. Now in the maximal reduction, when we consider, then it will introduce the concept of minimal sufficiency. So I'll introduce this through partition and then through the statistic. Okay. So let me start with a partition P is said to be minimal sufficient if, so first thing is that it is sufficient, and second is that if P star is any other sufficient partition, then P is a reduction of P star. So now it is clear. Among all the partitions which are sufficient, we consider which is a maximal reduction. So P is maximal reduction. Okay. So then it is called minimal sufficient partition. So now what is the minimal sufficient statistic? Which will induce the minimal sufficient partition. So a statistic which induces the minimal sufficient partition is called a minimal sufficient statistic. So we may alternatively define a minimal sufficient statistic T as satisfying the following two conditions. That first, T is sufficient, and second, if S is any other sufficient statistic. Then T is a function of is the definition clear? We start with the minimal sufficient partition and then minimal sufficient statistic. So of course they are in one-to-one correspondence with each other. Given a minimal sufficient statistic, we can find a minimal sufficient partition and vice versa. Okay, so is this definition statement clear to you?
Yes, sir.
Now the question comes that how to implement it. Okay, that means how to say that a particular statistic is maximal reduction. See, in the factorization theorem, somehow we are coming to the minimal sufficient statistic, but that is not a proof. We are just saying that it is minimal sufficient because like sigma xi or product xi, we are getting there. But those are for straightforward problems. There may be more complex situations where it may not be obvious. So there must be some theoretical method which will say that if you apply this, then you will get a minimal sufficient statistic. So fortunately, such method has been developed. So these sufficiency concept and minimal sufficiency, of course, it started in 1920s itself when the basic concepts of statistics were developed. The concept of minimal sufficiency was developed little later by E.L. Lehman in 1950s. Okay, so he wrote a series of papers in which you can actually look at this journal Sankhya where it is published 1950, 1955, etc. He has written few papers on this. So the method to determine minimal sufficient statistics. So it is better if we introduce a partition. So that means we should introduce a relation through which a partition can be defined. So let us consider. So let x have. So we will write x means x1, x2, xn basically. If you want, let us put it properly so that there is no confusion here. We have a random sample usually x1, x2, xn. So let x1, x2, xn have joint probability density function or probability mass function. We will use some notation, say fx theta. Okay, so theta here is theta 1, theta 2, theta k belonging to theta. So sample space is some x belongs to some space script x. Okay. In general, it is a subset of Rn. So let x and y be 2 points in x. Okay. So we say that x and y are equivalent, and we will write like this. Equivalence notation we will use like this. Okay. If the ratio fx theta by fy theta, that means we write at two different points, is free from theta. So if this ratio is free from theta, we say that the 2 points in the sample space x and y are independent, are equivalent. Okay. So first of all, we see that this relation is an equivalence relation. I think all of you are familiar because in your school algebra you have done equivalence relation, that is symmetric, reflexive, and transitive. A relation, if it is reflexive, symmetric, and transitive, it is said to be an equivalence relation. Okay, so let us look at this reflexivity, because if I consider fx theta by fx theta, this is one that is free from theta. Okay, so every point, that is x, is equivalent to x, so that is reflexive. Okay, let us look at symmetry. So x is equivalent to y, it implies fx theta by fy theta is free of theta, which implies fy theta by fx theta is free of theta. So y is, so this is symmetric also. Let us look at transitivity. So let us consider, say, x is related to y and y is related to z. Okay, then let us consider x and z. So if I consider fx theta by fz theta, we can write it as fx theta by fy theta into fy theta by fz theta. So this is free from theta and this is free from theta because x is related to y, x is equivalent to y and y is equivalent to z. So these two are free from theta. So this implies that x is equivalent to z. So thus this relation is an equivalence relation. Okay, so is the proof understandable to all of you?
Yes, sir.
Now an equivalence relation will partition the sample space into equivalent sets. This relation will partition the sample space X into equivalent sets. Okay, we will use the notation, say, D's. Okay, because we don't know this number, like how many sets will be there, that we cannot determine because this is an abstract framework I am writing. So I'll just write D's. Okay, it could be D1, D2, D3 and so on, or it could be over uncountable and so on. So we don't know what kind of sets are these. I'm just writing that. So for each point X in the sample space, define dx is equal to the set of all those y's which are equivalent to x. Okay. So for a given set x, given point x, consider all the points which are equivalent to that x and call that set as dx. Okay. So x belongs to dx obviously because of the reflexivity. Also, if x belongs to dy, then this implies that y will belong to dx, because this means y is equivalent to x, so x is equivalent to y. So in this case, dx and dy are same. That means for two equivalent points, you have one set. Okay. So, and also we consider one particular special case, that is the points where the density is 0. Okay, because there will be points where the density is not defined. Okay. So now each of these, it lies in some set D, and these D's do not overlap. So they form a partition. Let me call it partition to be pi of the sample space. Okay.
Sir?
Yeah.
Sir, can you explain what you said above? Like, if x belongs to x bar belongs to this d of x.
Yeah. Let me
Sorry, d
again.
of y.
Okay. Yeah. So I am considering all those points which are equivalent to a given point. So suppose I say x is a point, and all the points y which are equivalent to that, I put them all in one set. Okay. So obviously x is equivalent to x, so x definitely belongs to dx. And another, suppose there is another point y there, then the corresponding dy set, if you consider, then that will contain x. So therefore, because of the symmetry and transitivity, dx and dy will be the same sets. Okay, that means for two equivalent points there is one set. Okay, they will be in the same set. Then remaining, of course, there is a point. I mean, there are certain places where the density is defined to be 0. I mean, like we define, no, like exponential distribution, it is defined on the positive real line, negative real line, it is 0. And similarly, beta distribution, it is on the interval 0 to 1 and so on. So the remaining part I put into D0 set. So now each x lies in some set D, and D's do not overlap, because if x belongs to dy, then y belongs to dx. So overlapping will not be there. That means the points which are not equivalent, they will be in different sets. Okay, they will be in different sets. So this becomes a partition of the sample space, because this is equivalence relation. So this is the partition that is. So is this part clear till now?
Yes, sir.
So what is our aim actually? Because our aim is that we defined minimal sufficiency through partition. So now I have constructed one partition, and how that partition is induced? It is induced through the relation that if fx theta by fy theta is free from theta, then x is equivalent to y. So this relation is inducing the partition. So we will try to prove that this partition is minimal sufficient. So first of all, we prove that okay, so for each dx So for each partition set D, we will consider one representative point because it contains all equivalent points. Among the all equivalent points, I will just choose one point. Okay. So let us denote this mapping by that is G is the mapping of that is X. So that is from X to basically dx, and then from this to xd. Okay. That means from a given point X, I get dx, and I choose one representative point xd there. So this is some sort of mapping. Okay. So gx is a statistic. Basically, this gx is the statistic which is inducing this partition. So now let us consider actually we will leave out this d naught from here because at d naught the density is 0, so we need not bother about that thing. So fx theta is, we write it in this particular fashion. It is kx gx f gx theta. Basically, it is kx xd fxd theta. So this point I write like this, and I write this where I will write here this term which is I can write it now like this. This particular thing I can write as hx, and this one I write as g of gx theta. So where this hx actually I am calling to be 0 if x belongs to d naught, and it is kx gx if x does not belong to d naught. Okay, so let me explain what I have written here. See, if you consider this here, x belongs to D and xd is the representative point in D. That means x and xd, they are equivalent points. That means fx theta by fx d theta, it is free from theta. If it is free from theta, then it is simply a function of x and xd. Okay. So I am writing this here. So this assignment of x to xd, I am calling function gx. Okay. Here it will be gx here. There is a bracket here which I missed here. So this xd I am writing as gx. So this becomes exactly the factorization theorem. Okay. Because maybe I will write it in a slightly elaborate fashion. Is this argument clear to you, or if it is not clear, then I will write in a little more detail.
So please write in little more detail.
Okay, okay, I think it is better. I'll just okay. So Consider fx theta by fx d theta. So then this is free from theta. And so equals a function of x and xd alone. Okay, this ratio will be a function of x and xd alone. It is free from theta. Okay. So this implies I can write fx theta is equal to kx xd f xd theta, which I am calling now as hx, and this part I will write as g of gx theta. Okay, because this xd is nothing but gx. Okay, so there this hx is now kx xd, that is gx, if x belongs to does not belong to d naught, and it is 0 if x belongs to d naught. So, and this g of gx theta is nothing but f of xd theta. So gx is sufficient using factorization theorem. And what is gx? The partition pi was induced by g, because from pi only I have constructed g. So pi is a sufficient partition. All right, is this proof clear? Sufficiency of the partition pi.
Yes, sir.
Now the second step is that if I have another partition, then this partition will be a reduction of that. So that is another part. So let me start with. So let us consider hx to be another sufficient statistics. And let h induce partition. So let me call it, say, pi star or something like that. Okay, pi star with partition sets. So there I wrote the partition sets D. Let me write partition sets D star here. Okay. We must show that each set D star is contained in some set D. because the partition pi must be a reduction of pi star. Okay. So now let us choose 2 points x and y belonging to some E. Okay. Let me not put Ex here because just I'm writing E. Okay. A particular partition set. Okay. So here this means that Hx and Hy are same. Okay. Now we will use the sufficiency. H is sufficient. So we will write fx theta is equal to some alpha x times say beta of hx theta, but hx is equal to hy, so we can also write it as alpha x beta hy theta. And if I consider fy theta, then I can write it as alpha y beta of hy theta. So if I consider the ratio, that is fx theta by fy theta, in this one it will be only alpha x by alpha y. Okay, which we can just write as say some q of xy. Okay, that is free from theta. So x is equivalent to y in the sense that they belong to same D, same set D. Okay. So I started with one set E and I took 2 points of that, and I am able to show that they belong to same set D also. So from D star, we have gone to D. Okay, I made a small mistake here. Yeah, this is not E, this is D star. I just use a different notation here. D star here. Thus, this set D star is contained in some set D. This is related to partition pi star and this is related to partition pi. So pi is minimal sufficient. Okay, so is this proof clear? Is the proof of minimal sufficiency clear?
Sir.
So in order to implement this result for different distributions, what is required? What is the statistic which is inducing the partition equivalent? That is x is equivalent to y. So that means if I find out the function for which fx theta by fy theta is free from theta, then I will get that as the minimal sufficient statistic. So this is giving you an exact procedure of determining minimal sufficient statistic. So in the factorization theorem, you have seen that you are able to reduce, okay? But which reduction will be the maximal, that will be proved by this one. So let us look at the applications here. So we will look at all the standard distributions and see that the result is coming as per the. So let us consider, say, x1, x2, xn be a random sample from, say, Bernoulli. Okay, so let us write down the joint probability distribution. It is p to the power sigma xi 1 minus p to the power sigma. It will become n minus sigma xi. I am not writing down the first the density of 1 and then, because we have done these exercises many times now. We did it for the maximum likelihood estimation, we did it for the Rao-Kramer lower bounds, and then we did these calculations for factorization theorem and so on. So every time same type of statements will be used. So I'm not writing the full details here. I think you should not have any difficulty that. So if I consider the ratio this divided by fyp, okay, at 2 points, then this is p to the power sigma yi 1 minus p to the power n minus sigma yi. Okay, so basically 1 minus p to the power n will cancel out. What you are left with? You are left with p divided by 1 minus p to the power sigma xi minus sigma yi. Okay. So now when is this free from p? This is free from p if and only if sigma xi is equal to sigma yi. So that means the statistic is sigma xi is minimal sufficient. So the partition of equivalence is induced by Tx is equal to sigma xi. So now you can say that sigma xi is minimal sufficient here. So we have a formal proof of this statement. Is that okay? Now similar thing you can see for various other distributions that we have already worked out, like Poisson distribution, geometric distribution, negative binomial distribution with 1 or 2 parameters, with gamma distribution with 1 parameter or 2 parameter, normal distribution with 1 parameter or 2 parameter. So maybe I will write 1 or 2 exercises here and then remaining you can do yourself. Okay. So let us consider, say, for example, so this one I am leaving as an exercise, okay, because this is very similar. Geometric P. So this one again I am leaving as an exercise for you. say negative binomial R and P, and R is known. Okay. So this also you do it yourself. This should not be difficult. So let me take this uniform distribution. Okay. Let me write the solution here. In fact, you have already seen in the factorization theorem, we have written the form of the joint density, etc. So from there itself, it will be clear. So fx theta is 1 by theta to the power n, indicator function of xn from 0 to theta. Okay. So if I take the ratio, then this is 1 by theta to the power n, indicator function of 0 to theta yn. So again, this gets cancelled out. You are left with this. So this will become free from theta if and only if xn is equal to yn exactly, because there is no other way, because this is 1 if xn lies between 0 to theta, and this is 1 if yn lies between 0 to theta. So if their ranges are different, then this will not be free from theta. So only if they are exactly same, so this will be free from theta if and only if xn is equal to yn. So Tx is equal to xn is minimal sufficient here.
Here they should be equal because it is dependent on theta, is it?
Yeah,
Like
so
the indicator function.
Indicator function is also dependent upon theta. So when these two, that is I xn 0 to theta and I yn 0 to theta, when they will be equal, if and only if xn is equal to yn. In any other case, if the ranges are different, because it is equal to 1 if xn lies between 0 to theta, the denominator is 1 if yn lies between 0 to theta. So if xn is not equal to yn, then the range of that will vary, and then it will be dependent upon theta. So to make it free from theta, you have to have exactly xn is equal to yn. There is no other way. So that's why I'm writing if and only if. So that means this function Tx is equal to xn, this induces this equivalence partition on the sample space, and therefore this will be the minimal sufficient statistic. Is that okay?
Yes.
Yeah, so I mean, I think I have explained the concept very properly. In fact, since you already know how to write down this joint PDF, because that thing now we have done several times in likelihood estimation, in the lower bounds, and then in the factorization theorem. So everywhere you have written the joint densities. So I mean, this should be a very straightforward exercises how to derive the minimal sufficient statistic, because the concept of equivalence partition now I explained to you. That means you write the density at two different points, that is fx theta and fy theta, and when is this ratio free from theta. So it will give a necessary and sufficient condition that gives the sufficient statistics. See, please remark my word properly. I am saying if and only if, because suppose I say x1, x2, xn is equal to y1, y2, yn, then also this is free from theta. But then that is not minimal sufficient. Okay. I am looking at the maximal reduction. So if and only if. Okay. So that is very important. Okay, so let me just write now one or two exercises for your practice. So x1, x2, xn following normal mu sigma square. Okay, we have done this exercise for factorization theorem, etc. So tell me the minimal sufficient statistics in the three cases. Okay, what is the minimal sufficient statistics? Yeah, I mean, we have already done the factorization theorem, so you should be able to tell me the answers very quickly.
So for case 1, it is sigma xi.
Okay.
For case 2, it is sigma xi minus mu square.
Yes.
The case 3 is sigma xi comma sigma xi square.
Sigma xi and sigma xi square. And a one-to-one function of this is x bar and s square. So we can write this also. Because one-to-one function of a minimal sufficient statistics will also be minimal sufficient. For example, here you can write x bar also. Okay. All right. So I think you are able to understand this thing very clearly. So let me just write other problems also. So exponential mu sigma, that means I am taking the density to be of this form, 1 by sigma e to the power minus x minus mu by sigma, where x is greater than mu, mu is any real and sigma is positive. So again, you have to find minimal sufficient statistic. Okay, so find out for this case also, at least tell me the answers here.
Case 1, it is again sigma xi or x bar.
sigma xi r x bar. Okay, yeah. Second one.
Second one, any stat, like it is always independent of mu, right? So what shall we take?
It is not always independent of mu.
X order one.
x1.
X1 will come because in the indicator function that will
Should be greater
come.
than mu.
Yeah. And the third one.
X1 and sigma x.
x1 and x bar.
Once again, we write one-to-one function of this also, like x1 and x bar minus x1. Actually, there is an advantage of writing this because the distribution property of this one comes nicely. So that will come when I will tell you how to calculate the expectations, and because we have to do the inference. So for the inference purpose, so I am writing this alternative also here. Here you see I am writing one sample x1, x2, xn from normal mu sigma 1 square, and another random sample y1, y2, yn from normal mu sigma 2 square. So the mean of the two samples is same, okay? And these samples are independent, okay? Samples are independent. Again, so independence I am taking because for writing down the joint distribution, you need the product, okay? So find the minimal sufficient statistics here.
Can you explain this question again?
So I have a random sample x1, x2, xm from normal population with mean mu and variance sigma 1 square. I have another random sample y1, y2, yn, which has again which is from normal with mean again mu, but variance is different, sigma 2 square. Okay. So actually, I will tell you this is actually an important problem in statistical inference. It is called the problem of a common mean or common parameter. So initially it started with some design of experiment problems in 1940s, where you had two different estimates for the same parameter, and the two estimates were coming in independently. So now, of course, you can find large number of applications. For example, if I have a certain measurement problem and I have two instruments to measure, okay, but they may have different precision, okay. One may be very good, one new machine, and another one is an old machine, and I am taking the readings on the same thing, okay. So if I am taking the reading on the same thing, then the average reading must be the same, isn't it? That is, mu must be the same. But I have two different estimates. It is also possible that I have different ways, like when the data collection is there, then there are different independent observer groups are framed. So in order to eliminate the bias of different observers, we need to combine the information from different samples, because maybe that X sample is in a particular way, Y sample is in a particular way. They may be by biased this one. So if I combine them, then I can eliminate the bias. So this became an important problem in statistical inference. In particular, in 1958, actually two statisticians by the name Frank Graybill and RB Deal. So they actually produced some estimator which combined. So for example, if I am using the first one, then I will use, for example, X bar. If I am using the second sample, I will use Y bar. But then they produced an estimator which is combining these two, something like S2 square, or you can write like this. it was written in this particular fashion, like x bar divided by s1 square plus y bar divided by s2 square divided by 1 by s1 square plus 1 by s2 square. This type of weighted mean of x bar and y bar was taken, and it turned out that this is also unbiased and it has variance smaller than the variance of x bar as well as the variance of y bar, provided the sample size is at least 11. So it became a very powerful result and it led to a lot of work in this area. So after 1958, there are papers in 1960s, 70s, and so on. And then even like me and my scholars, we have done a lot of work in this particular area for other distributions here. So this is a problem of common mean. So this has some special structure also. Another part of the structure will come little later. Firstly, let me find the minimal sufficient statistic. So I am asking you, you firstly derive this minimal sufficiency, and then I will go to some special features of this one, which makes this problem statistically, you can say, a complex as well as challenging problem. Okay, so I will come to that little later. Firstly, find the minimal sufficiency here. So you have to write the joint distribution of x and y samples. Is the problem statement clear?
Yes, sir.
Yeah, please find the minimal sufficient statistics. Okay, so are you able to get it?
Sir, sigma 2 square by sigma 1 square sigma. Sorry, sigma xi minus mu whole square.
Sigma xi minus. What did you say?
Sigma of xi minus mu whole square.
No,
Multiplied
mu
by the
cannot
ratio.
come. See, this is parameters are unknown. No, mu sigma 1 square, sigma 2 square are unknown. So these are all parameters. Okay. So sigma xi minus mu cannot come there. In the statistic, parameter will not come. Okay, so could you get it? Okay, could you get it now? Okay, could you get it?
No, sir.
So we need to write down the joint density of all the observations. Okay. So firstly, let me write for x, then it is 1 by root 2 pi to the power m sigma 1 to the power m e to the power minus 1 by 2 sigma 1 square sigma xi minus mu square. See, these things you have to remember because we are doing repeatedly same type of things. When I wrote the likelihood function, when I wrote the Rao-Kramer lower bound for the information, when I did for the factorization theorem, we have written the same type of term. So that should not be difficult. Now the second term you have to multiply here corresponding to y sample. Okay. This is yj minus mu square. Okay. So this is the complete density function here. Of course, because we need to take ratio and then cancel out some of the terms. So therefore, it is better if I write it in a little bit elaborate fashion. So let me write the constant terms here. Root 2 pi to the power m plus n, and then we have this sigma 1 to the power m, sigma 2 to the power n, and remaining things now let us split out. That exercise also we have done earlier. For example, you expand this xi minus mu square, so you get xi square minus 2 mu xi plus mu square. So if you do that, you will get terms like this: e to the power minus m mu by sigma 1 square, mu square plus sigma square, minus n mu square by sigma 2 square, and then remaining terms will have x and y terms. So that part let us write carefully. So e to the power sigma xi square by 2 sigma 1 square with a minus sign minus sigma yj square by 2 sigma 2 square, and then you will have this mu xi term. So m times that will become, we can write here mu sigma xi, and 2 will get cancelled out. So by sigma 1 square plus mu sigma yj by sigma 2 square. This is all in the exponent. Do you understand this calculation? Because I have not done anything new. Whatever expansion we had written earlier for the factorization theorem, etc., I have written the same thing here. Only you have to write carefully all the terms.
Yes, sir. Clear.
So now you write it at another point because this is at xy. Now you write at some x star y star. So if I write f x y mu sigma 1 square, let me put all this theta as mu sigma 1 square sigma 2 square. Okay. So let me put it here, theta divided by at another point say x star y star theta. Okay. So this outside term will get all cancelled out because this does not involve any x, y. You will get ratio of these things only. So e to the power it is coming. E to the power you will get sigma xi star square minus sigma xi square by 2 sigma 1 square plus sigma yj star square minus sigma yj square by 2 sigma 2 square plus mu by sigma 1 square sigma xi minus sigma xi star plus mu by sigma 2 square sigma yj minus sigma yj star. Is this term clear? The constant term I have cancelled out in the numerator and the denominator, and remaining part I have written properly. And from here you can derive the necessary and sufficient condition for this to be free from the parameters mu, sigma 1 square and sigma 2 square. Can you observe and tell me what is the condition? What is the necessary and sufficient condition?
Sigma xk square, sigma yk square, and sigma xi and sigma yi.
So you get this entire thing. This is free from theta if and only if sigma xi, sigma yj, sigma xi square, sigma yj square is equal to sigma xi star, sigma yj star, sigma xi star square, sigma yj star square. Okay. So minimal sufficient statistic is that is sigma xi, sigma yj, sigma xi square, sigma yj square. This is also a one-to-one function of x bar, y bar, s1 square, s2 square, where s1 square is sigma xi minus x bar square 1 by m minus 1, and s2 square is sigma yj minus y bar square divided by n minus 1. Okay. I hope this is clear.
Yes, sir.
Okay. Next we introduce. So one thing is clear now because of the Rao-Blackwell theorem, that if we want to find out estimators, we should base it on sufficient statistics. Among the sufficient statistics, we should base it on the minimal sufficient statistics. Okay, that is the maximum reduction of the data can be utilized for the purpose of statistical inference. So that leads us to substantial savings in terms of complexity of retaining the data, maintaining the data, and utilizing the data, because all other information can be removed from the system. That is not required here. Now, yeah.
Sir, how come the sigma x square and s1 square are one-one functions? In some cases,
They are not one-to-one
for
function. This entire thing is a one-to-one function. See, this I am calling t, and let me call this as t star. Okay. Then t and t star are one-to-one functions. See, given sigma xi, sigma yj, sigma xi square, sigma yj square, I can determine x bar, y bar, s1 square, s2 square, and given this one, I can determine this. Because what is this one? This is nothing but sigma xi square minus m x bar square, isn't it? And what is this one? Sigma yj square minus n y bar square by n minus 1. So if this is given, if T is given, then T star can be determined. If T star is given, then T can be determined, isn't it?
Yes, sir.
Isn't
Okay,
it? Actually, this looks more, you can say, attractive, because for the purpose of inference on mu or sigma square, we will actually generally prefer x bar, y bar, s1 square, s2 square, rather than the raw sums and sums of squares. Of course, for calculation purpose, those things are used, but for the purpose of utilization of statistics, it is better to use the means and the variances. Of course, if you go deep into the inference, then you will know all those things. This is only the starting course, so you will know only a few things right now. Okay. So one thing is this sufficiency, and which leads to minimal sufficiency, something like a, you can say that best possible situation kind of thing, you can say. Okay. Along with that, there is another concept which was again developed by these people only, Lehman and Shafi, actually, in 1950s, which made this combination of completeness and sufficiency as, you can say, one of the very, very profound concepts in statistical inference. So let me talk about that now. Okay. So it is again due to Lehman and Shafi. Okay. Actually, they wrote some papers in 1950s. Okay, which were published actually in the Indian Journal of Statistics called Sankhya, which is published from Indian Statistical Institute. And these results became very famous because of immediate applications. So you will see that. Let me introduce the concept first. So let us say X be a random variable with probability distribution. We'll give some general notation. Okay, P theta, where theta belongs to theta. Of course, this parameter theta can be scalar or vector. So if you want, you can write in general also theta. Okay, it's a some k-dimensional parameter in general. So we say that the family of probability distributions I will give the notation P. Okay, so P theta, where theta belongs to theta, is complete if expectation of gx is equal to 0 for all theta and any function g implies that probability that gx is equal to 0 is 1. So if this condition is satisfied, then we say that the family of probability distributions is a complete family of distributions. I am making a very, very strong statement. I am saying that if expectation of a function of random variable, so basically function of random variable means statistic. Gx is a statistic. So if expectation of a statistic is 0, then that statistic itself must be 0 with probability 1. If such a thing happens, then the family of distribution is said to be complete. Then a related definition will be, because here I said, okay, x is a random variable with certain distribution. So we can also say that x is complete, okay? We also say that x is complete. So family of distribution is complete means family of distribution of this random variable x is complete, okay? So the two things are used synonymously. So now in a given problem, if I am saying random variable x, we are taking a sample from there, that is x1, x2, xn. Okay, then we are considering certain statistics, suppose sigma xi or x bar or sigma xi square, etc. Then that also has a distribution. If that distribution is having a completeness property, then we will say that statistic is also complete. So a follow-up definition is let x1, x2, xn be a random sample from some population, and let Tx be a statistic. We say that the statistic T is complete if the family of distributions of T is complete. Because the definition of the family of distributions being complete I have already given. So if I can find the distribution of T, and with respect to that family of distribution, if the completeness property is satisfied, then the statistic will be complete. Okay, so let me start with some examples, and then let us see that what is the significance of this. Okay, first of all, is the statement clear to all of you? If there is any problem in understanding the statement. Is the statement clear?
Yes, sir.
Okay. Okay, so let me start with some applications. Again, we will write the same densities, okay, whatever things we have been considering as standard distributions. So firstly, let me start with one Poisson distribution, okay. Say x following Poisson lambda. So we will try to prove for this, okay. So consider G such that expectation of Gx is equal to 0 for all lambda, okay. So I am writing down this statement, expectation of Gx is equal to 0 for all lambda. So I will like to prove that Gx itself is 0 with probability 1. So you look at this condition, it is Gx e to the power minus lambda, lambda to the power x by x factorial, x is equal to 0 to infinity. So I am saying that this is 0. So this e to the power minus lambda is a positive quantity, so I can multiply by e to the power plus lambda on both the sides. So that will give me gx by x factorial lambda to the power x, x equal to 0 to infinity, that is 0 for all lambda positive. Okay. So this function I can call something else. Let me call it hx. Okay. So what you are getting on the left hand side, it is a power series in lambda. This is power series in lambda, and we are saying it is becoming 0 for all values. Okay. And it vanishes on r plus, that is the positive half of the real line. So this is possible if and only if each coefficient is 0, that is hx is 0 for all x. That means each coefficient is 0. Now hx is nothing but gx by x factorial. Since x factorial is never 0, this means gx itself is 0 for all x. Actually, the Poisson distribution has the probabilities devoted to the points 0, 1, 2, and so on. So if there is a function which is 0 on these points, this means that the probability that gx is equal to 0 is 1. So that means the family of Poisson distributions. So the family of Poisson distributions, that is Poisson lambda, lambda positive, this is complete. Okay, so first of all, is this proof clear?
Yes, sir.
Now let us go to the initial statement here that x1, x2, xn is a sample from Poisson lambda. For this problem, the minimal sufficient statistic is sigma xi. So if I consider Tx is equal to sigma xi, that is minimal sufficient. So I would be interested in the completeness of this. Okay. What is the distribution of Tx? What is the distribution of Tx? Yes, please tell it again. Please tell what is the distribution of sigma xi?
Poisson
Yeah, Poisson, but with what parameter?
n lambda.
Poisson n lambda. So if lambda is positive, n lambda is also positive, isn't it? So if the family of these distributions is complete, this is also complete because the same type of statement will come. Oh, what happened? There is some disturbance here. What happened? So if that is complete, then this is also complete. Okay. So Tx is a complete statistic. Okay, is this statement clear to you?
Yes, sir.
So now let us extend these things to different distributions. Suppose I say X follows Bernoulli distribution, or say binomial distribution, okay? Binomial NP. Then expectation of Gx is equal to 0. Okay, here N is known and P is the parameter. Then this statement will become Gx NCx P to the power x into 1 minus P to the power n minus x. So if you look at this, this is again similar kind of a statement, because if you see this term, this is having x, and these terms, if you expand, what type of terms you will get? P to the power 0 into 1 minus P to the power n plus P into 1 minus P to the power n minus 1, and so on. In fact, you can write it like this also. Suppose I remove this end points here in the interval. In place of this, I write this one only. Okay. So I can write like this Gx NCx, and I can write it as something like eta to the power x is equal to 0, where eta is P by 1 minus P. Okay. So this is nothing but a polynomial of degree at most n in eta. And if P is between 0 to 1, then eta will be positive. Okay. So we are saying that this will vanish on R plus if and only if all its coefficients vanish. So what are the coefficients? Coefficients are Gx into NCx. NCx is never 0. So that means Gx is 0 for all x is equal to 0, 1 to n. But the binomial distribution gives the positive probability precisely to these points. So this means that the probability that Gx is equal to 0 is equal to 1 for all P lying between 0 to 1. Is that okay? So the family of binomial distributions is also complete. So if I am considering, say, a sample from Bernoulli trials, then some of the Bernouillian trials or mean of the Bernouillian trials, that will be complete. Let us take a little bit more difficult example. Here what we have used the uniqueness of the power series or the uniqueness of the polynomial, because if it is equal to 0, then over an interval, then it should be identically 0. So some uniqueness property we have used. In the case of continuous distribution, we have to look at the argument little bit in a modified way. So I think all of you are familiar with Laplace transforms, etc. You have done a Laplace transform course, some of you or none of you? Let me take an example where that concept will be used. Okay. Have you done Laplace transform? Yes or no?
So can you revise it once so that it will be full?
Uh-huh.
Just say the rough part of it so that you can recall it.
Okay, Laplace transform is defined like this. Suppose I am having a function, say gx. Okay, then the Laplace transform of this is defined as e to the power some tx minus tx dx from 0 to infinity. This is called Laplace transform of the function g. Okay. Since you have already done the moment generating function, so I think you don't have to bother that much because this is similar to that. Only thing is in the moment generating function, we write the density into e to the power tx, that is expectation of e to the power tx. And then we write over the range of the distribution. Here it is written 0 to infinity. So this is a special case, basically Laplace transform. We have done the moment generating function in probability course, and a further generalization of that is a characteristic function, etc. Again, the uniqueness property is there also. So basically that will be used in the proofs here. So let me give the first one here for this normal distribution. So if I consider expectation of gx is equal to 0 for all mu, how the statement will be written? That is integral minus infinity to infinity gx 1 by root 2 pi e to the power minus half x minus mu square dx is equal to 0 for all mu belonging to R. Okay. So expectation of gx is 0. So now you write it in slightly better form by expanding this x minus mu square. So this is gx, this 1 by root 2 pi I can remove, and then you have this e to the power minus x square by 2 e to the power minus mu square by 2 e to the power mu x dx. This is 0 for all mu. So e to the power mu square by 2 I can take outside because this is a constant and also positive, and root 2 pi I have already removed. So this is nothing but some hx times e to the power mu x. This time I am writing as hx. Okay. So this is equal to 0 for all mu. So even if you are clear about the moment generating function's uniqueness, probably that property was told to you in the class in probability and statistics. So this is nothing but something like a moment generating function of this function hx actually of this distribution. Of course, here hx is not necessarily a density function. That is why I was trying to use a more generalized form, that is Laplace transform, but it's all right. So this is again unique. So for the distribution for which it is 0, then it is 0. Therefore, here also this should be 0. So this means hx is equal to 0 for all x. Okay. So that means probability that hx is equal to 0 is 1. So this family of normal distribution is also complete. So I will give you some more exercise here. If I take sigma, then that this is complete. Okay. Let me take another example. say uniform distribution. This distribution is important because it is slightly non-conventional. The standard form of splitting the distribution, etc., does not hold here. Here the density function is written as 1 by theta for 0 less than x less than theta. So if I consider expectation of gx is equal to 0, then this implies that gx by theta so this theta I can remove from here because this is a constant. I can take it outside and multiply on both the sides. This means integral of gx dx is 0 on every interval 0 to theta. So that means if I take theta is equal to 1, theta is equal to 2, theta is equal to 3, theta is equal to pi, theta is equal to e, theta is equal to 1.4 and so on. For every real number theta positive, this integral is 0. This is true if and only if gx itself is 0. That means probability that gx is equal to 0 is equal to 1. So the family of uniform distributions is also complete. Okay, is this clear?
Yes.
Yeah, maybe I will stop here because I did not take a break here. So because we have to give then examples of various distributions, what are the complete statistics in all those distributions, and whether everything is complete. I mean, there may be something which is not complete also. So that also we will have to find out. And then what is the use of this? So actual use is that in the estimation problems, we get the best procedures based on that. So that is the main thing, like optimal thing we will get. So at this point, let me stop here. Do you have any questions? Do you have any questions?
Sir, what is the physical, physical significance of the completeness?
Okay, I mean, I will explain to you maybe in the next class, but right now, what you understand here is that if I am taking a function whose expected value is 0, then basically I am saying that function itself is 0. Okay. So basically, it means that the only unbiased estimators of 0 are 0 itself. That there is nothing else. Okay. So this will actually lead to some sort of uniqueness property. And okay, so in the estimation, when we consider the unbiased estimation, we will see that in most of the problems, unbiased estimators are unique, and therefore they will become minimum variance unbiased estimators. So this is actually a very, very interesting thing, because ultimately, what is the purpose of this inference things that we are doing? In the distributions that we are doing, generally what we are getting, the procedures that are being obtained using the likelihood procedure, lower bound procedure, generally you will see that they will coincide to the best, or you can say optimal. So because of certain inherent structure that is coming. So what is the inherent structure? Inherent structure is sufficiency and completeness in most of the standard problems. So actually, the popular distributions or whatever that is, they are being used in statistics. So it is something like you say that why such distribution is only used, nothing else is there. So if you use this, what is happening is that you are actually concluding to some optimal procedures. And so I will tell in the next class about the direct application of this, which is in the form of finding out the minimum variance unbiased estimators. Okay. Any other question?
Sir, you said there is only unique unbiased estimator.
Yes, yes,
There will
yes.
be many. There will be many. Sir. Like we have seen examples which two.
Yeah. So yeah. So I will just tell you what is the meaning of uniqueness there. Once we discuss that thing. So for example, if I said in the Poisson distribution, so the family of Poisson distribution is complete. Now if I am taking a sample from there and I am considering sigma xi. So sigma xi is having Poisson n lambda, and in that family again it is complete. So basically you can say x bar is a complete statistic and it is minimal sufficient. So based on the minimal sufficient statistics and complete statistics, I will use estimators based on x bar. Now, is there any other estimator other than x bar itself which is unbiased? Answer will be no. You can say that okay, x1 plus x2 by 2 is unbiased or some other thing, but then that is not based on the sufficient statistic. Okay. So based on the complete sufficient statistic, there will be a single unbiased estimator. So then we should actually use that. So not only in the unbiased estimation, in fact, in the other optimal estimation, when we are even dealing with the biased estimators, we will consider procedures which are based on the complete and sufficient statistics.